All right, so we got two more factors to go that affect the stability of the conjugate base. Okay. All right, so this one is called inductive effect. I'm going to explain what an inductive effect is in a bit. Right? But let's see this first. So we have three acids here. Who's the strongest acid? Well, if you don't know what to do, draw out the conjugate bases. All right, always draw out the conjugate base. I'll take a look. So we have this a negative charge on oxygen, but this guy attached to chlorine, attached to bromine, attached to iodine. Okay. Now what's happened here is surprisingly, the chlorine, bromine, iodine play a little role in here, right? And the relative acidity is relatively big. If this guy's one, this guy 200 times stronger acid, almost 3,000 times stronger acid than the iodine one. Yeah. How come though? Well, let's talk about inductive effect. Okay, so the electronegative atom nearby can affect the stability of the negative charge, right? And that's what we call inductive effect. But what is inductive effect exactly? I'll give you an analogy here. Anyone here is a Harry Potter fan? Have read or watched Harry Potter? This guy is what his name? So either whatever, Dementor. Yeah, Dementor. What does he do? Is so he will if he catch you, he will suck happiness out of you and you died, basically, right? The inductive effect does something like that. I'll take a look here. Okay. Now we have a regular alcohol, and an alcohol with the 3 fluorine in it. Look at the acidity different there. Okay. What it does is this 3 fluorine will help, not really, it's kind of suck the electron density out of the oxygen, but it's kind of help stabilize the negative charge, just like that. Pull electron to itself because of high electronegativity, which means that this oxygen doesn't have to carry the weight of the negative charge by itself. Fluorine help oxygen do that. All right, and the relative acidity, look at that, almost 3,000 times different than this regular alcohol. All right, I have another example. Take a look. We have acetic acid, pK about 4.7 something, about 5. Right, we have chloroacetic acid, dichloroacetic acid, and trichloroacetic acid. The trichloro 1.7. This guy is a strong acid. You know that this two. The more number of chlorine, the stronger the acid there. And the reason the same thing, because more chlorine stabilize the negative charge, right? If you compare to just the structure of acetate, this oxygen carry the weight of the negative charge by itself. Actually, not it got a resonance there, but everyone else has a resonance, so that doesn't count here. Okay, and once it got the one that have one chlorine group, chlorine is pull electron to itself, help oxygen carry the weight of the negative charge, right? 2 chlorine pull even more pull, and 3 chlorine even more pull. Now this guy is relatively a strong acid. Okay, the most stable, the strongest acid there. All right. So an electronegative atom helps stabilize the high electron density region by withdrawing electron through sigma bond. This is through sigma bond right here. Through sigma bond. Okay, and that's the reason why the inductive effect decreases over distance, right? So look at this this acid here. Okay, we have a alpha position, beta, and gamma position. If the chlorine at gamma position help the oxygen stabilize the negative charge just by a little, so from 4.8 to pKa go to 4.5. If chlorine get closer to beta position, 3.98, go to alpha position, 2.83. Okay, so 4 bonds away, 3 bonds away, 2 bonds away. The closer, the more inductive effect. The further away, the less inductive effect. Okay. All right. Now, I got a common mistake or a lot of question on this. All right. Think first. Who's the strongest acid here? Ta-da! Who's the strongest acid? Most, not I wouldn't say most, about half of the students would say that the one with iodine is the strongest acid. But that's not true. That's not really true, right? Some people get confused using all those factors together, but here's what you have to think about it. We start using the size, the electronegativity and size first, if you still remember, okay? We use the size and electronegativity. But the size and electronegativity has nothing to do with the stability of these conjugate bases. How come though? Well, the negative charge is on oxygen. All of them have the same size and electronegativity. The negative charge is not on iodine, right? A lot of students think that, oh, it's iodine. Size matter here. Size, the bigger size, the more stable the conjugate base. Well, the negative charge is not on iodine. It's on oxygen. You can use size here, all right? So size and electronegativity don't work here. You can't use that here. Right, so you got to look at the size and electronegativity of the oxygen, and apparently they all have the same size. So size and En doesn't do anything here. Okay. Next one, resonance. Do they have resonance? Yes, but all of them have the same resonance. So resonance doesn't help here. What's the tiebreaker? The inductive effect, induction. Fluorine is the most electronegative atom here. Will be able to pull electron. Help these two oxygen stabilize the negative charge the best. All right, so carry the weight of the negative charge the best here, and that's the reason why pKa of fluoroacetic acid is the lowest, 2.66, the most acidic here. All right, iodine, the electronegativity of iodine is not as good, so 3, around 3, doesn't help as much. All right, so watch out though. You have to look at what atom is carrying the negative charge. Can you use size? Can you use En or not? All right, but in this case doesn't do anything. They're all oxygen. They are the same size, same electronegativity. You gotta use the inductive effect here. All right. Okay. All right. Another one. So this kind of example, you're gonna see this group we call a nitro group, like nitro. The nitro group is the most electron withdrawing group, like the best one there. Look at the pKa. Same, just replace iodine, fluorine with the nitro group, and the pKa from 4.7 when goes down to 1.68. Okay, and if you still remember the phenol, so the special alcohol we talked about, so pKa about 10. If you put a 3 nitro group onto the benzene ring, we call pyrric acid, 0.38. This guy is a strong acid. All right, and you probably have heard the trinitrotoluene, we call TNT, which is explosive substance, right? These two are really explosive, really reactive, right? Because of the nitro group down on there. All right, one more factor.